It's my great pleasure to have our prominent distinguished lecturer today is Professor Cheng Zhuo, okay, from the Zhejiang University. So let me first introduce Professor Zhuo and first, okay, and Professor Cheng Zhuo, he is currently a professor in the School of Micro-Nano-Electronics at Zhejiang University and serves as the director of the Institute of Computational Intelligence. He received his bachelor and master degree in electronic science and engineering from Zhejiang University in 2005 and 2007 respectively, and the PhD degree in computer science and engineering from the University of Michigan Ann Arbor in 2010. His current research interests focus on hardware intelligence, machine learning assisted design automation, and low power designs. He has published over 150 technical papers and co-authored 3 books in those areas. Dr. Zhou has received 7 Best Paper Awards and Best Paper nominations at conferences such as DEC, ICCAD, and ASB.TEC, as well as 2 International Design Competition Awards. He is currently Associate Editor for IEEE TCAD, ACM Todas, and Elsevier Integration the VLSI Journal. He is a fellow of IET and a senior member of IEEE. Okay, thank you. It's our pleasure to have you, Chen. So all the time, the rest of the time will be yours, please.
Okay, yeah. Thanks to me. Thanks for the introduction. It is a great honor to come to CEDA, this forum, and to discuss about our recent work. And so we have something I want to attract audience, so we call it FabGPT for smart IC manufacturing. We want to discuss the challenges we see and also some potential solutions. So IC manufacturing actually is a very crucial aspect of semiconductor industry. So this is a typical IC product flow. You can see we have design, manufacturing, and test. If the products cannot meet the specified the specs, it will go back and to modify design. Typically, this process, especially the manufacturing, is very expensive, and also the production time is very lengthy. I have some numbers. If you can see here, for 55 nanometer, the fabrication is around 0.3 million, and this number goes to 14 million for 7 nanometer. And of course, for 5 and 3, this is even higher to even billions of dollars for each fabrication. On the other hand, the manufacturing time is very lengthy. So Intel has a very famous rule of the tick-tock, which means for every technology node upgrade is like 2 years. But now at like after 7 nanometer, fabs cannot really maintain this pace. The major technology node upgrade actually takes much longer and longer, to 2 to 4 years. So on the other hand, as we can see that we have AI, which is innovating very fast. It's almost every day. So we can see there's a great gap between the semiconductor industry and the AI industry. So here, let's go back to manufacturing and take the wafer defect detection as example. Wafer defect detection is actually one step for the within the semiconductor manufacturing. So in addition to wafer defect detection, there's like the also the WAT and other tests. And the wafer defect detection, it uses like the scanning electron microscope images of the wafer surfaces. After certain process steps, I have a flow here. After some steps here, the defect detection system will take the wafer image, as you can see here in the middle. And then some die level pictures will be taken and investigated. Typically, this detection is done in a manual procedure, and the very experienced engineers will look at location and type of defects, and then trying to understand where the defect is from. It's from some process issues or from some residues or from some environment issues. Then they will try to improve the process for the yield ramp up. So this highly rely on the expertise and also the internal methodologies built upon that. And in addition, this is not cheap. So for operational costs, that includes the energy and personnel cost is about like $1 million per year for even a small team. And there is also like $5 to $15 million for equipments, depending on its low end or high end machines. Even with all those costs spent, the productivity actually is not that high. Engineers can only process 100 plus wafers per day, even if they do that for even if they put all their time on this defect detection job. On the other hand, even for a small fab, if it wants to maintain some like a budget balance, it needs to process maybe like 1,000 wafers every day. So you can see like this is only like 10% of all the products they produced. So there's a huge gap. Because of all those gaps, people will think that can we do something smarter, like using the machine learning or deep learning technologies? However, there's very limited research on defect morphology, which is the best way to identify the particular process step issues. A couple of reasons. So you can see here for the 4 figures on the very left, the different morphology actually can be of the same defects. So for the first 2, they're both scratches, but they can have quite different shapes. And then you can see for the particular, for the row of the particles, they also look different, but are of the same defect type. On the other hand, even the defects can be from different categories. Meanwhile, they can have very similar morphology. You can see the particle and in-film and scratch versus in-film. They look similar, but they are from different sources. So the last but not least, the background can be very complicated, which actually makes the problem more difficult. So the engineers or some vision-based algorithms, they need to overcome all those challenges. They understand if this issue is from some abnormal image in litho or some material residue during etching. So that's a very challenging task. For human beings, they can be very subjective depending on his efficiency and also on his experience. And it's also very high cost. For those vision-based algorithms, we actually see very high false defect detection rate. And it's also difficult to really perform root cause analysis by just looking at those images. So we want to do something even smarter than that. So can we really deploy like the large language model or some deep learning algorithm to this? Then there are a few challenges we should address. The first one is that IC manufacturing is actually a small data. So this is actually a common issue that has been met for many industrial domains. The amount of data is very small. Meanwhile, we want to something that is smarter than the human being. So this is actually a conflict. But in addition to small data, we have quite a lot of modalities data. Each is with different dimension and amount, like the technical nodes, like the databases. So, but those multimodal information cannot be easily aligned. On the other hand, because we are talking about IC manufacturing, as you know that the fab can be quite private. The privacy is definitely a concern. So it needs like the deployment on the edge. Meanwhile, the large language model inference is expensive. So how to make the deployment of such a large language model on the edge is another challenge. In addition, we want the procedure to be very efficient, but development cycle and cost actually increase significantly for sub-7 nanometer. So the agile development and deployment is another challenge. So we can look at all those challenges in some more details. So the first thing is the small data. Actually, we have a large quantity of data during manufacturing, but it's good in quantity, but low in quality. Because to maintain the stable production line operation, the manufacturing process actually has very limited variability. So even with large quantity, we cannot really achieve a very good AI model from such low quality data. On the other hand, during the TD, the variability of data actually is high. However, at that step, the quantity of data is low, and also it's very expensive to collect the right data. So that's the fundamental challenge we are seeing in the IC manufacturing. So of course, there are quite a lot of progress in data augmentation and generation. Unlike the similarity-based approaches, data augmentation generation methods can expand the training sets by generating or synthesizing new samples so that we can improve the model performance even in a small data environment. However, for this particular problem of the defect detection, actually it's very easy to get overfitted and bias a pattern because of the lack of diversity and realism. So another thing I want to talk about is modality. So here is a very good example we can see here. If you can see in the middle, there is a picture of a cat with a hat and a dog with a beanie. So if we just look at a picture, we will be wondering if we want to identify the cat versus dog or the hat versus the beanie. However, if we can look at this picture with some text prompts, like a photo of a cat and a photo of a dog, then we can easily know the comparison between the cat and dog. So that's how the text prompts help with the image. So such multimodal information is definitely very helpful. Such as text, we tend to give a better answer with those modalities. However, the issue here is that for the IC manufacturing, the heterogeneity of data, like dimension and volume, actually can be quite different. For example, you may have only like 1,000 or 2,000 wafer images. Meanwhile, you have like 1 or 2 technical nodes for some processes. On the other hand, because of dimension and volume is so different, it's very difficult to synchronize and align those data. And the last thing is that when we want to look at the key features from some modalities, the experience is actually very important. The human being experience is very important for such a cross-modal interaction. So how to overcome those challenges is another issue. Recently, there are a few works that are looking at the multimodal defect detection. So they want to identify and analyze the flaws or irregularities in the products or materials to ensure the quality and reliability. Usually, the modality is between the visual and log files and reports. And the very first one is called Anomaly GPT, which is the first multimodal language model for industrial anomaly detection. It's not particular for semiconductor engineering, but the model itself can actually identify and localize anomalies and answer some questions. However, the poor multimodal feature extraction actually makes the detection of small wafer defects very, the efficiency is very low. Meanwhile, actually, it cannot answer anything else in addition to the particular question. So the last thing I want to talk about is deployment. Deployment is always difficult for large models. The large language model has shown significant size growth in the past 5 years, with the parameter increased maybe 15,000 times from 330 million to almost 10 trillion. Meanwhile, we can see on the right that the computational capabilities still lag far behind, which almost like 10,000 difference. So this is a huge gap. So we definitely need to see how to do more efficient deployment to ensure that the large language model can really be carried out for some hardwares. And this is actually, I didn't see this quite different from what we do for other deep learning models. But now we are really dealing with a much larger model. So people can do quantization. from, for example, from the FP32 to Int8 to achieve like lower computational workload and memory access and power consumption. Recently, there are quite a few works to work on the LLM specific accelerators to ensure it can collaborate, it can work well with all those new quantization techniques. Some quantization techniques will go to the very extreme, like the binarization, which is, of course, the most the lowest number we can go with the number of the bits. In addition to quantization, people will also look at the sparsity-based optimization. So basically to look at the unessential computations and remove that in both the self-attention and FFN modules. So this requires parameter fine-tuning of LLM to reduce the accuracy loss due to the sparsity, which is also very expensive. And in addition, there's some like unstructured sparsity and not very sufficiently hardware friendly to get accelerated by hardware designers. And for those LLM specific accelerators, actually people are building like a software, hardware co-design system. So this actually demands some agile SoC design space exploration. When designing such a system, we can use DSE method to reduce the modeling overheads to ensure that the software and hardware are in sync. However, because the LLM is so huge, and this complex workflow, many complex workflow actually make this DSE very difficult. There are some flows like the deep and ZDA LLM. This actually will result in exponential workload increase without necessary modeling and optimization. And there are also some open source workflows like what I show on the left. And those workflows actually are easier, like the ChipYard, Gemini, they can support an agile design flow. However, the issue with the agileness is actually the accuracy. So there is like also a conflict between the agileness and the accuracy, how to ensure that we can do agile DSE, meanwhile, the model and optimization is sufficiently accurate is another challenge. So after I review all those works, we want to build something that is for smart IC manufacturing. Of course, currently we are only addressing the issue of the wafer defect detection. And we want to do this from both the algorithm side and the hardware side. And this is like an infrastructure, we call it FabGPT for smart IC manufacturing. And I will talk about some interesting findings during this journey. So on the algorithm side, so we actually need to address the issue of the small data and the multimodal and also the lack of the specialized knowledge. So with all those issues addressed, ideally, we want the model to not only detect the defects, but also do the reasoning, why this happens, and also to ensure that what processes or which processes cause this issue. So that's the target of what we want to do with the FabGPT algorithms. So the infrastructure is a little bit complicated, but here, because of time, we want to limit to a few key technologies like the multimodal input, the feature enhancement, alignment, and so how we process the complex background. So for the multimodal input, we have the visual input, which is the SAM image, and also the textual input, which is the text prompts as the general inputs. However, in addition to that, what we want to, because the amount of data is so limited, so we really want to delve into more information. So one thing we want to delve is like the text mark on those SAM image, as you can see here on the very lower left. So this actually leaked information like the log ID, device ID, and those informations. We can convert those text marks through the OCR techniques into some additional text prompts. Another thing we actually provide to the large language model is the text templates. This can actually be considered as the abstraction of the specialized knowledge from the senior engineers. So we have like two levels of the this template is like a template library. This will ensure that when we describe the same image, it will give you a template. So later, the LLM needs to do is to fill in this template. For example, you can see here, when we describe the flaw or describe the defect, we just make sure that it can only select a bunch of keywords from this library, like the linear scratch or facial scale shape scratch, so on and so forth. So in addition to that, we also have like a template level prompts, which actually describe the same image capture quality, such like a blurry photo, a dark photo. As you can see on the lower right, this state is what needs to be filled in. By doing this, actually, this is like a template library. It will be provided as like the input to the large language model, and it does need to be updated. And however, during the large language model interpretation, it will try to use the correct template to fill in the right keywords. And then this actually make the interpretation and also the understanding of the image much simpler compared with the generic interpretation. So another thing is the multimodal feature enhancement. So we need to distinguish the complex image features and enhance the key features, which can be very challenging. So here we develop a prompt learning-based feature optimization technique to extract the image and the text features and achieve the semantic consistency. We here use a prediction module to extract the defect attribute informations, which is called PN. And this can be further used to enhance the multimodal feature. Then we use the pre-trained expert adapters for images and texts, utilizing the semantic prompts to strengthen the relevant features and reduce the redundancy. So this approach actually efficiently control the feature flow and quality and enhancing the overall efficiency. So the third key technology that I want to talk about for this model is the feature alignment, so which is very critical. We here utilize the Q-former to align the multimodal features. So in particular, we actually use the cross attention to align the cross-modal features to improve the local detail capture. And then the feed-forward network generates unified multimodal features and enhance the cross-modal information sharing. In addition, to eliminate the modality bias, we also design a similarity calculation module to compute a factor A, which helps balance the multimodal tokens. By doing this, actually, the FabGPT can not only answer the wafer defect detection problems, but can also answer some generic questions related to IC manufacturing. And then we also have like a mixed data training approach to balance the new and known knowledge and integrate this IC domain expertise. So the last technique I want to point out here is how to mitigate the impact of the complex background. Here, actually, we propose like a dual path module. This module actually, in addition to compute the QK attention, we also compute something called VV attention, which is the self-correlation of the value V. And then this helps us to focus on, helps the model to focus on semantically the similar or related areas to avoid the distraction from the irrelevant regions, which is the complex background in our case. And we have this V branch in parallel with the QK branch, which creates a dual path block. And this is and multiple dual path blocks will be cascaded together to form an encoding block and then used in this large language model. So I want to show some results on the algorithm side. So this is first is some Q&A. As you can see on the left, we have some defect rated expert Q&A. For example, we give the FabGPT the queried input and raise some question like what is this defect and how this defect looks like, and can you tell me the root cause of the defect? And the FabGPT can give its answer very efficiently. Meanwhile, we also have something irrelevant to defect detection, but related to IC manufacturing, as you see on the right. Some prior works to ensure that the large language model can answer the specific domain, the question from specific domains, actually they limit the knowledge. So it's kind of like they cannot answer anything else in addition to some particular types of questions. And by doing in our FabGPT, we can answer both defect-related questions and IC manufacturing, as you can see on the right. So it can even answer something like how can AI aid the development of IC manufacturing, those very generic questions. The second result I want to show is that the comparison with the non-LLM baselines and the comparison with LLM baselines. So basically, when we provide some SAM images, the FabGPT will try to find out where the defect is and do some segmentation. Here I show the original image, the ground truth, and some other models, the non-LLM models like DeepNet, DIA, and for LM baselines, we tried GPT and LISA. Both are like the multimodality models. For the other multimodality models like LISA and GPT, we see that it actually get distracted a lot by the complex background and cannot really segment well for some small defects. Meanwhile, the FabGPT can actually they can utilize the provided specialized information well and to align the text prompts and with the image to do better segmentation. So the third piece of the result is the accuracy comparison in a quantitative way. We look at image AUC, pixel AUC, PRO, and AP, and compare with other models. And here I think I selected a few models. In our paper, we have like a more comprehensive comparison. So basically, the FabGPT actually outperformed the other models. And similar, and for the results on the lower left, you can see that's the accuracy comparison for different questions. It's like the question of the presence, the defect category, location, quantity, description, analysis, and unrated question. So it is noticed that the green bar is actually the GPT-4. It's the older version between 4.0, and the red bar is the FabGPT. So I think what is most interesting is that after GPT-4 is doing pretty well, even in this very specialized and narrow domain. So we try to understand why the GPT-4 is doing so well. So we actually do a little bit more comparison here. You can see here. So for detect, you can see here for the first column is the detection and localization. We raise the same question and for the same image to both GPT-4 and FabGPT. You can see the answer here. The GPT-4 can give some ambiguous answer, which is kind of correct, not accurate, but kind of correct. Meanwhile, FabGPT can give you more accurate answer. Some information is, of course, the GPT-4 probably they have some like a training material which related to SAM image. And another thing we see is that we find out is that GPT-4 actually utilize the text marks, which I mentioned in the very beginning, which is some small fonts on top of those SAM images. Actually, GPT-4 will read those text marks and then try to understand the content of the image and then to link the image and question to the correct answer. So if we remove the text marks for those SAM images, and we actually see that the accuracy, the precision and accuracy of the Q&A actually goes much lower for all those questions, detection, analysis, and model assessment. So the second part of my talk is on the deployment side. Actually, we see how want to do the efficient inference of binarized LLM and agile SOC development. So the large language models are typically based on some transformer architecture. which can be memory intensive. And if we look at all the operators for a large language model, we can see that the matrix and the matrix vector multiplication is the most expensive one. Meanwhile, the normalization and activation only accounts like 18%. So the key issue is that if we can optimize such matrix intensive memory and computing intensive computations, there are quite a few works that try to quantize the transformer architecture or large language model architecture to some extreme, which is the binarization. After binarization, they can do some retraining and tuning to achieve still maintain pretty good accuracy. Some papers report that the accuracy loss is less than 1%, and some papers show like less than 5% for those like the Llama 2 and those large models. And in our deployment flow, the major contribution is that one is the how we binarize and pack the FP to the binary values. And we also have some hardware-aware model optimization and compilation to ensure that the model can be efficiently deployed. And then we have some agile fidelity-driven optimization to further optimize the large language model to ensure the software and hardware is really in sync. So first, let's look at binary quantization. So in a binary neural network, both the weights and activations are constrained to either +1 and -1, and then packed into integers. So the vector multiplication is implemented using the XOR operation followed by a population count. As you can see here for the figure on the lower right, so we have like a 64 by n, which is the FP32, such a vector. After binary quantization, actually we get a bunch of the binary numbers, and then we can do the data packing into like n integers. Each integer is in the 64. So by doing this, actually, we not only reduces the computation overhead, but also helps mitigate the stress on the memory. So then for the figure on the very right, you can see for this multiplication, it's just the XOR operation and the population count. So with such like a binarization, binarized accelerator, we actually do something like mixed data precision, because we are aware that if we binarize all the operators, then the accuracy actually is very low. So we want to identify the key operators and then do the right binarization. Meanwhile, the other operators can still maintain the floating point. So for the figure on the top left, you can see that's what we identify. So basically for those matrix multiplication and matrix vector multiplication, for those operators, actually we do binarization, and the others we still maintain the floating point. Then we design a dual accelerator with mixed precision. We have a 4 precision accelerator systematic array, and which is process all the 4 precision floating point operations. Meanwhile, we have like a binarized accelerator, which is process the binarized operations. A RISC-V core is used to schedule the data and also do the packing, depacking, and quantization, dequantization operations. So the key point is how to identify the right operator and assign the proper precisions, and also how to ensure that the large language model algorithm is right in sync with the underlying hardware. Here to ensure very fast deployment of large language model, we here propose like a fidelity-driven method. So fidelity here is like the precision of a model approximates the real world data or phenomena. So we're trying to, as you can see on the right, as we go to the ladder design stage of an IC design, so basically from RTL to netlist to the post layout, actually we get higher and higher accuracy. Meanwhile, the complexity also goes higher. So what we want to do is to build some fidelity correlation between the RTL to pre-layout to post-layout. So at RTL level, we want to do some very fast computation, which of course is with a low fidelity. And then at the pre-layout level, we have some middle fidelity results. And finally, at the post-layout, the fidelity is the highest. So if we can build a correlation between different stages, then even at RTL level, we can kind of estimate what the PPA will look like. And this will give us more accurate estimation of the selection for the design parameters. And then we can do more efficient optimization. Of course, it's always challenging to build such a link from the low fidelity to middle fidelity to high fidelity. So what I want to point out is the mapping here is not really trying to map to find out the exact accurate numbers. Instead, we are trying to accurate which one is better. We want to compare two design options or two design parameter options. If option A is better than B, we will go to option A. In this way, actually, this lower down the requirements of the mapping accuracy. So this is so then we can, after we construct the performance mapping between the functional simulation, pre-layout simulation, and the post-layout simulation, we can build such a the LLM algorithms and the hardware all put together in the same loop. In this way, we can build a very comprehensive flow to understand how the SO design, model compilation, and optimization will impact the final results. And meanwhile, we can also switch between the different simulators. We can even use the function simulator like Spike to analyze the communication cost and also the parallelism to provide more accurate cycle level reports. And this framework will provide very high scalability and good configurability. So we have some results on the stability, as you can see here. Here we utilize binarized processing elements. The FP32 int 8 int 32 actually refers to the precision, the multiplier used. And then the 8-bit, 32-bit, and 64-bit refer to how we pack the binarized numbers. So we evaluate our binarized accelerators against the baselines with different precisions. As you can see here for the figure on the left, for different array size, 4x4, 8x8 to 32x32, the packing size of the 64-bit actually achieve a similar area in comparison to the one of the integer 32. Meanwhile, the performance actually is much higher because actually we are it's like a 64-bit packing. We are only processing the binarized numbers. Similar to the area comparison, you can see the power number on the right. The number of the 64-bit packing, which is the red bar, achieves the lower number in comparison to the FP32 and the similar number as the 32-bit for different configurations. And we also compare the stability when with the increased model size. This study actually illustrates the pre-layout performance of our design with the increasing sequence length for the two transformer layers. So the attention head is equal to 1 and 8. So for the figure on the left, you can see that the capability of our design to process the long sequence actually is very efficient, which is a crucial performance metric for the LLM. The figure also shows that the latency increasing trend is significantly lower than the increasing of the sequence lengths. So for the 1 to 32, which is like a 3 times sequence length increase. So we only, I think the latency number is only increased less than 2 times. And for the figure on the right, we actually look at the scalability for different workload. So as you can see on the x-axis, we have something like 32, 1, 32, which refer to the matrix multiplication shape. It's the matrix of 32 by 1 times the matrix of 1 by 32. We use the first case as a baseline. As you can see that for different tasks from the left to right, with the right one is the 32 by 16 multiplied by the matrix of 16 by 32,000. The workload increased almost 32,000 times. Meanwhile, you can see that we have the red one and also the brown one, which refer to the 16 by 16 and 32 by 32, the array size in our accelerated design. Basically the computational cost increase is much lower in comparison to the workload increase. This actually shows the good scalability of the proposed design. So finally, we want to look at the comparison of the runtime profiling. As you may recall that at the very beginning, we showed that the majority of the runtime is spent on the matrix vector multiplication and the matrix multiplication, which is almost 80% of all the runtime. After the binarization and all this SOC design optimization, the matrix vector multiplication only consumes about like 56% of the overall runtime. Meanwhile, the normalization time and the activation time is increased, and also we need to spend more time to do the quantization, dequantization, and also some scheduling. So the last thing I want to show is the comparison on the model performance. So here, actually, we compare the results with NVIDIA Orin, NVIDIA Nano, RK3588, which is basically an SoC platform that includes like the GPU, NPU, and the CPU, and also the Raspberry 4B. And those results are all measured on the real boards. So we look at the models of the Llama, Transformer, OpenAI GPT-1, and the MadGPT, and for all different configurations. As you can see on the latency wise, I mean, the figure is a bit small, but the last column, the blue column is the optimized design from our work. So basically, it can achieve much higher performance in comparison to the NVIDIA Orin or to the other boards. It's only slower than NVIDIA Orin. Meanwhile, the NVIDIA Orin consumes significant higher power and area. So NVIDIA Orin is actually very strong and power hungry. So if we look at numbers, the proposed design is about 1.77 times faster than Nano and almost 10 times faster than RK3588 and Raspberry Pi. So this is all about the inference results. So finally, I want to briefly summarize the talk. So smart IC manufacturing is very highly designed for the IC industry. However, the issue is still the small data and also the privacy of the data. And there is a limited expertise availability, and also the design and manufacturing complexities. From what we discussed with a few local fabs, the senior experts is very limited. So basically, they cannot really conduct the defect detection all day long. These tasks had to rely on the junior engineers or inexperienced engineers. And so we believe that something like FabGPT can actually act as a good infrastructure. It can help to abstract the expertise knowledge and embody those existing EDA tools. And then it can act as the infrastructure to do the Q&A, to do the root cause, and debug, and also some flow management. Of course, this is the long-term goal for this work. Currently, we are only look at the Q&A and also defect detection. And but we hopefully in the future, this can be a good user interfaces to the designers, technologists, and also the teachers and students. So that's what I have for today. So any question?
Okay, thank you for Professor Zhuo for this comprehensive talk. Yeah, it's not just originally I intend you will talk about the software side, but later you talk about deployment. I think it make this talk very comprehensive, and also the FabGPT cannot just use for the IC manufacturing. I believe you can use this can be used for other applications. Yeah. Okay. Yeah, so everyone, if you have a question for the Professor Zhuo, please type message in the Q&A boxes. Okay. Yeah, so before that, I have a quick question. Yeah, do you plan to open source of your FabGPT?
Yes, we plan to do that. Yeah.
Yes. Yeah, I think that would be very helpful for the community.
Yeah. We really hope that more people will join us to really promote such an infrastructure. Because we really see the need from the fab side. I believe for a large fabs like the TSMC, probably they have a bunch of the senior engineers, but for the small fabs or some fabs working on the mature technologies, actually, it's very difficult to have a senior engineer to stay for long term. You know, the workload of the fab is actually pretty high. Right, and we also see the necessity for students to really understand what the manufacturing is doing. We hope such things can be helpful for them. Yeah.
Mm-hmm. Yes. Yeah. You cannot always rely on those old experienced engineer, right? You need more tools. Yeah. That would be very helpful for the company. Yeah, and the community. Yeah. Yeah. Not sure if questions. I think right now I have type one question from Giovanni on. Yeah, I think same question about the open source. Yeah.
Okay.
Yeah.
So.
Can you? Yeah.
Oh, so it's the Q&A.
Yeah, in the button you can.
Yeah. I think basically the FabGPT is an infrastructure. You can always associate it with open source and commercial EDA tools. As I show from my figure here, because I think the EDA tool actually, most EDA tools actually are pretty good. It cannot be really simply be replaced by the deep learning or AI algorithms, but it just depends on how you use them, right? So this is what a large language model can do here. It has its role is the infrastructure, not the replacement. Yeah. What other hot topics are in AI-driven TCAD apart from LLM-based TCAD? So that's actually a very challenging question. For the AI-driven TCAD, actually, I mean, TCAD, I think there are a couple of things. One is the real-time TCAD, how to make a TCAD to run very fast. So you really need to embody some AI to see if you can some more efficient behavior model instead of just solving those differential equations. And also, I believe there are quite a few works in the past few years in DAC and ICCAD talking about the PRN-based work to really to speed up the TCAD simulation. However, most of the AI-driven TCAD, I think they are still kind of constrained by the generality and also the training cost. If the cost is too high, actually, it's difficult to replace existing commercial tool. And if it's not general enough, it's also difficult to do that. I think that's the bottleneck and challenges that need to be addressed in the future.
Mm-hmm.
Of course, I would also like to look at how we can really have have some interaction between the LM and TCAT, because TCAT is another issue with TCAT is it's really a very difficult tool to use. Yeah, so it really also depends on a lot on the experiences. The boundary conditions and all setup, it's challenging. So if we can use the large language model to abstract some expertise knowledge and make the use to be easy, the usage to be easier, and I think that's also a very good and promising direction.
Totally agree. Yes.
Okay.
Again, I think there's still one question from the same from Giovanni. Yeah.
Okay.
So if
Would
other
AI-driven semiconductor device simulators be easier to work on than AI-driven semiconductor management process simulators? Only because it is simpler and we have to model less steps. So I think both are. I think both simulators actually I work a lot on simulation side, so I believe both simulators are actually very challenging, because they have the similar issues as I said earlier, the generality and also the training cost. And I think for the AI driven, instead of AI driven, I think it should be more like the AI assisted. I still think the simulator itself should rely on the original one, which has been tested and verified for many years, and its accuracy is very reliable. Because for simulation, one thing is that how to ensure the results are reliable. It's usually for the manufacturing, also the last few steps of the design. And so AI is actually can be used to assist such simulators instead of drive such simulators. That's my own opinion. It probably can help you to skip a few steps or to find a good some reordering option during the simulation, during solving. So that's my opinion, yeah. And from the problem, I think both problems actually are equally challenging.
Right, different dimension. Yeah.
Right.
Okay. Yeah. So I think we still have time to take one or two questions if anyone, would like to ask questions for Professor Zhuo. Okay. Yeah, and I have to tell everyone that after the talk today, we will put a recorded video, okay, on the on the CEDA presentation library. Okay, so if you like to look into the detail of Professor Zhuo's talk, so you can. I think we will put the video on the CEDA YouTube channel. I think after 1 or 2 days. I think, yeah. Okay, and I think again we have a question from a very diligent Giovanni. Yeah, so Cheng, can you?
Okay. Oh, that's a question. I see.
Yeah, there's one more question. Yeah, I think
For students with access to semiconductor manufacturing with EUV, this software, can we use open source device simulator from? I think open source simulators are actually, I think the difference between the open source and the commercial device simulators really depends on the skill and under some change in boundary conditions. The accuracy will be different. But I think for students, if you want to understand the phenomenon of some simple structure, that should be sufficient. Yeah. But if you want to use for like complicated and add some advanced technologies, definitely there could be some difference. I mean, even the commercial simulators, they need to migrate and update from technology to technology.
Okay. Okay, thanks, Professor Zhuo, for the wonderful talk. Yeah, for today. And I think if everyone, if you have a question for Professor Zhuo, please send email to him. And as I mentioned, we will record a video. And Laura just mentioned that the video will be put on the CEDA website on Monday. Okay. Yeah, so I think that's all for today. And Giovanni asked the last question. Zhen, do you want to reply the question? Yeah, I think that's a short question. You can.
Okay.
Yeah.
Waiting to use open source device setup. I think that's an interesting question.
Yes.
I think it's really depends on the quality and innovation of the idea instead of simulator. Yeah. So if you use some good ideas that can work with the open source device simulator and it can prove its efficiency, I think the people will buy the idea. Yeah.
Yes.
It
I
doesn't
think
really
this.
need to be like a commercial one. Yeah.
Yeah. I
And
think
I
this is.
believe that many papers are on the open source side, right?
Okay. Okay. Thank you, Chen, and also all the attendees. Thank you for coming for today. So I would like to close the session for today, and thank you for everyone. Especially thanks for Laura and also Professor Zhou. Okay. Thank you.
Yeah. Thank you. Yeah.
Thank
Bye.
you. Bye.